Hello everybody, welcome to a special episode of TechStack. I am with Jim on site at Qualcomm, and we have a very special guest coming up next. Welcome back, everybody. We are with Alberto Martinez from Qualcomm. Jim and I are here learning about the Snapdragon X2 Elite, which was announced at the Snapdragon Tech Summit. At this event, we're getting a much deeper technical dive, and we're going to have a conversation with Alberto and learn even more, and hopefully pass some of this on to you. So, as we start, why don't you tell everybody your background and what you do at Qualcomm?
Yeah, very good. Well, thank you for having me first. It's always a pleasure. For me, getting to Qualcomm has been a little bit of a long journey. As an immigrant, I came to the United States in 1990, right? And with a passion for technology and the desire to do something super cool that can change the world.
Yep.
That was my hope and my aspiration. I was fortunate enough that at the time I was hired by Epson initially, and then by Intel Corporation, where I spent 26 years. I call it graduated from Intel in 2020. I did pretty much everything that can be done in an SoC, from the firmware to the software stack to the architecture, the technology development, the innovation, and ended up managing the technical content of the whole SoC for a couple of years, couple projects. When I officially retired from Intel. At that time, Microsoft had this aspiration to have a very competition against Apple, buttress the ecosystem in a stronger fashion. So I had a good relation with Pavan Davaluri, and he reached out and said, "Hey, why don't you come and help us at Microsoft? And tell me why you wanted to be your role." And he said, and we agree that my role will be helping to architect the SoCs that the ISVs were doing in order to buttress the Windows ecosystem with more power efficiency, move into the AI era. So did that, and the results of that effort at Microsoft was the Snapdragon X Elite, the original design, which it was the first Copilot plus PC architecture that was deployed. Then the codename, as always known, Lunar Lake, right? And the Ryzen's that also came as a Copilot plus PCs. Those were the results. And I grew an affinity to the Qualcomm product for several reasons. First of all, the philosophy of power efficiency first. Yeah. Not that the others don't look at power efficiency as something important. It is, but in Qualcomm culture, power efficiency is the root of the innovation design. It's not part of the design; it's the root. So, with that in mind, performance become okay. If you are power efficient, how you develop performance? No, if you're performant, how you develop power efficiency. I love that philosophy very much. I also love the philosophy of a machine learning acceleration as a focal point on the architecture of the design. That was also the happening in the Snapdragon X Elite 1, right? That the machine learning acceleration is a centerpiece of the overall architecture and provide the capabilities that Windows use to develop their infrastructure for the features they have deployed so far, and new features that are going to continue to deploy in the near future that also were ported to other architecture. Enter Microsoft 2025 and the roadmap that we had created as taking shape. And the next question was for me, okay, where do I take this? And saying the reverse of that coin is also super important, which was, okay, Microsoft is leading the ISVs into a new architecture set for Copilot plus PC. Mm-hmm. But also the ISVs need to lead the operating system in the changes that are required to create that perfect match. So talking to Kedar, he said, "Hey, why don't you come help us here?" and I said, "Yeah, I'd love to do that." And came the role, the reverse polarity of that role. It became a software strategy, right? So which is looking at the hardware infrastructure that we have, the capabilities that we have, and how we establish a roadmap of progressing innovation that we can participate with Windows and other operating systems in order to develop a capabilities that will surpass what the competition is doing. And that is my role now. So I know hardware, I know software, I know firmware, and I try to be everywhere.
Well, given your...
That's a long answer for a very little
That's
question.
okay.
Really
That was
good
a
answer.
great introduction. And you've worked on so many of these SoCs for compute and for the PC market. You know, you
For
have a
decades.
very unique perspective. And, you know, just diving into the architectures, we're seeing it and getting all the details on it. This looks like a completely different PC architecture than we've ever seen before, especially in terms of, you know, just even the layout, how you lay out, where you lay out the cores, and, you know, scalability, you know, seeing like in the, so like the sensor island, seeing 7 different cores just to power the sensor island. Not to mention each one of these functions has so many different cores and functionality to optimize it through hardware, not just software. So, I mean, can you highlight maybe some of the key architectural details that make this so different from other PC SoCs that you've worked on in the past?
Yes, that's a great question. Thank you for asking that. It's a great opportunity. I'm sure Parag would love to answer that question, but he's not here, so I'm the best I can answer. So here's what I observe, because I didn't work directly in the X2 architecture. I did help in the X1 architecture from outside in. But what I found super interesting is when you look at a design and you put cost at the centerpiece of the architecture, you make quite different decisions if you put efficiency and performance at the centerpiece of the architecture, and then you solve for cost, right? So if you say, I'm going other companies will say, okay, you have 120 millimeters square to give me an SoC because that's what I can afford. Over here we say, okay, you have 10 milliwatts to solve this problem, right? Because that's what we can afford. And then you solve for, okay, all right, don't break the bank, right? You need to design it so we can sell it, right? And it created a different constraint environment. So a very interesting question I will ask today is, why did you put the third cluster of CPUs in the other side of the chip?
Mm-hmm.
And well, because it happened that if you make it pretty rectangular like that, the last core will be too far from the level 2 cache and from the SLC. Right, the level 2 cache on the cluster will be too far from the SLC. The distance between them will be different. So now you have to solve for timing to the worst common denominator.
Yeah.
Think about it. Now, if you rearrange it, that the distance is sort of within the constraint of the PV design or the timing path for some of your listeners that doesn't follow the terminology. If the timing path of one of the core is kind of so iso around your caches, then the result is you solve for the best timing possible, not for the worst common denominator, which affect the latency, affect the number of clocks that you need to spend on it, which affect power. So it was a very beautiful question. We just don't have enough time to answer the details, right, on that. There was another question on a GPU. Why your GPU seems to be smaller than the overall total of a core? That's an excellent question. If you look at the mobile PC market, look at your bracket of pricing, and then you ask a question, how much of a gamer population is on those segments?
Right.
Yeah.
Those segments are really productivity segments, entertainment segments. They are not fundamentally a gamer segment. The gamer segment will seek, a AAA gamer, will not use an integrated graphics.
Right.
No.
No, he or she will have integrated graphic and so for gaming as a casual thing when they're in an airplane for 13 hours, right? So they're bored and they're gonna whip up their laptop. They want it to work. They wanted to have 50 frames per second, right? They wanted
And
to
they
work.
have to be on battery.
It had to be on battery, and they had to entertain themselves for 13 hours. Okay, fine, right? We had to solve. right? In that segment. Eric would like to create the ultimate GPU, right? But you need to consider, as we are entering in the market, how you're going to enter a market, right? And how you're going to bring your value and your where. Well, you lean where you have the best capabilities, right? And you create a differentiating vector. So the GPU has to work. We have to solve for it. But for most users, right, they don't play games. We are not going to invest in, I don't know, 12 teraflops of gaming capability for something that is used less than 1%. So, okay, yeah, that's the answer, right? That is the answer. You have to look at your customers, the range, and remember, you have to now solve for cost, right? Right? So you solve for performance and energy efficiency, now you solve for cost. Where do you trade off? That is the answer.
That's actually a perfect segue for a question I had. The PC space relatively new for Qualcomm, and then there's different challenges when you enter a market, and there's incumbents that have been there for ages. How do you make design decisions on roadmap or on product when not only are you contending with incumbents that have been there forever, you have software challenges they don't have because it's a different architecture, and you're trying to achieve different things in terms of efficiency and battery life. Can you just give some insight into how you make some of those design trade-offs and how you make some of those decisions when you're putting a platform like this together?
Yeah, I think the answer to that question is I want to put it in a single short segment that you want to call fail fast. Right? You have to be quickly to experiment. You have to quickly to find the errors in your ways, and you have to be quick to recover from it. And don't be proud enough that you're going to preserve a mistake. Right? So one can make a decision in the roadmap, and that decision in the roadmap sound right? In retrospective, in the present might not be the right one. So then you had to, in a company like Qualcomm, that speed is everything. Something very impressive of Qualcomm is that they solve for speed. With that mean, once they understand the problem, they go quickly to solve it.
Sure.
Right? And they swarm it, and they get solved, and this gets solved fast. And that's one. Right? So you had to learn. You had to learn fast. One of the things that Kedar, Cristiano, Alex Kedar have been doing is hiring talent that had the experience. But one thing that I say to my peers that get hired from outside that coming to Qualcomm is start with humbleness, right? Be respectful of the past. This is a company with a long pedigree on technology, right? You're not going to tell them what they need to do. You need to listen what they're doing first. And then help with the gaps, right? Understand what are the gaps, and is there something they don't understand on the market and they're butting their head against the wall? Well, let's explain what the market is doing and why it's different than the mobile phone market. Why you don't sell through an ISP, right? You sell through a distributor. And they had different ways of life because they had done that for 30 years. So that type of things is part of the learning process that we're doing together, right? But be humble, learn the ways of the company, and then bring your value in, right? I have seen in other companies that have happened. I have seen it that the person that is hired externally to come in feel empowered to change their ways. Listen, there is a reason they do the things they do. Don't break what it works, right? Let's find out what they need first, and then let's help solving those problems.
Well, you talk about filling the gaps, and one of the gaps on the initial Snapdragon-based devices was manageability. So with the X2 Elite, now we have Guardian. So you're actually adding in a very flexible manageability platform, not just for enterprise, but also for consumers. I mean, that's a huge benefit.
I'm glad that you asked.
And the fact that it's not just hardware, but it's also software enabled.
I love you bring that up. I'm one of the initial culprits that designed the ANT architecture at Intel in my organization. And the ANT architecture was born when wireless still wasn't popular in a great advanced fashion, and cellular was still doing cellular in a computer was not understood. And ANT has evolved in that direction. The difference with Guardian is that it has been designed from the ground up for cellular communications. It's actually say, okay, we know how to do cellular communication to manage a device. We do it on the phones. How we do that in a PC? And yes, we had to do Wi-Fi and we had to do LAN-based interconnectivity. But is the whole concept for Guardian to be available all the time and be able to manage the device everywhere is super powerful. I'm super proud of what has been done there. It's super, super powerful.
It should open a lot of doors for you folks in the enterprise too. Really
one will hope.
Yeah.
One will hope. Enterprise is always difficult to enter. It's harder than consumer. Again, people are set in their ways, and they had a behavior. There's a network effect that occurs when there are incumbents in the market, and enterprise tend to be a stronghold for the incumbents. But we're bringing value that there is in different vectors, right? And those values in different vectors are appreciated by a certain portion of the commercial enterprise business, and we expect to have interesting and fast penetration.
Yep. So you had mentioned answered a question about GPU earlier. One of the things that I took away from today's talks was there was lots of talk on NPU. There's NPUs on a low power island. You have the big hexagon cores, and the GPU is a massive upgrade over previous gen for rendering and graphics workloads.
That's right.
But not a lot of talk about AI on the GPU, even though it's fully capable. What are some of the thought processes that went into putting huge development effort into NPU and sort of focusing on graphics with GPU?
Yeah, that is also a wonderful question. You probably hear Upendra Kulkarni's presentation that he went into certain level of functions has affinity to certain type of computational architectures, right? CPUs are great scalars and branch predictors where code jumps and go places that, unpredictably. So branch predictor value is like how well they can predict. That's not very convenient for internal because it's an overhead and gate counts and architecture elements that doesn't play in favor of a very structured architecture like a network, ML network. They're very predictable. You can know where it is and how you're going to dispatch it. Then on the other hand, you have the GPU, which is from scalar, we move to vectors. Now, you don't see a lot of scalars doing vector processing as a GPU. Think about it. Why? Because the reason is a scalar processor will have a significant number of clocks needed in order to do what a vector processor will do with few number of clocks. There are wider registers. In those wider registers, you can do things. It happened that a vector processor is better to do ML than a scalar processor. And it happened there was a company that took advantage of being in the right place at the right time with an architecture that works, right? It happens that way. To develop a software infrastructure that allow for their vector processors to be very useful, right, on AI workload training or inference. But it costs power. You're trading off power. The next level of acceleration is you create a matrix or tensor processor. So you go from scalar to vector to matrices, right? And matrices, multiple matrices computation is a tensor, right? As mathematical goes. So now you create a tensor processor, something that is dedicated to process the structures of an inference network. So people will say, well, the GPUs are getting better at that too. Well, I say, yeah, if you can get a GPU to be as efficient as an NPU that is dedicated as a processor for that function, you just rebranded an NPU. Right? If you can do that, you need to isolate your matrix multipliers or your vector processor from your shaders and renders, right, and ray tracing units in a way that they are really a bolt-in that had a common interface on top. Okay, so you just bolted in an NPU. Okay, you could do that, right? And people actually are doing that. Why are they doing that? Because they had a brand. Their brand is on GPUs. GPU is you had a hammer and you sell it well, but you call everything a hammer, right? But yeah, they're adding matrix multipliers and extended sync instructions and so on and so forth for the purpose of improving the power on the GPU's architecture. And can they get there? Now, GPU has something that they had established, a programming architecture that is popular, right? That's true. And that programming architecture was created to support vector rendering. It's separate from the CPU that also had a very popular programming architecture. And again, you don't see a lot of CPUs doing graphics. Had the architecture for NPUs evolved to the point that is satisfactory to everybody? Oh, okay, that is the proper challenge. Yeah. That is the proper challenge. It's not whether it's a GPU versus NPU versus CPU. It's what is the program architecture that brings the best value of the best architecture that you can deploy for performance and efficiency simultaneously. Now, to close on that, AI is not an application. People say AI application, but AI is not applications. AI is a programming model. Yeah. Yeah. It's a programming language. It's a very natural programming language, but it's a programming language. CPU will have a programming language. Microcontroller will have that programming language. From Arduino class devices to servers, will have that programming language. GPU will have programming languages, that programming language, and of course in NPU is the foundation where that programming language will run best for efficiency. So it will be everywhere. And there will be some population out there that will prefer to run in CPU because it's easy to run. And they have, I don't know, an AI fast Fourier transform or encoder that run well in a QMX-like matrix because it's running the ICE instruction of the CPU. Mm-hmm. Well, that's very powerful. Why not do it? Well, it will cost you power, but it's expeditious. Prototyping expeditious. You can get to it very fast. Some will decide that they had invested on GPU and the best way to get to deploy minus power efficiency is on a GPU. And some will say, okay, for me, like Microsoft had done with their infrastructure for Windows on Copilot Plus PC, is we choose NPU. Or we have chosen NPU for delivering the power efficiency. They actually have specific battery life impact numbers. They say, I cannot cross this line in battery life impact. Otherwise, I cannot deploy it. And you will see some platforms change the quality of the output based on meeting that performance goal, that power efficiency goal. No, that's not well known, but if you measure different platforms for the quality of the AI output, it's not the same. And once you ask a question at some point.
Interesting.
Well, Alberto, you know, we've talked about the Elite X2 being really designed for thin and light, and also in some of the designs we've seen for very small form factor desktop PCs or all-in-one PCs. But, you know, just like everything else that Qualcomm does, it seems like every part of that X2 Elite is really designed for scalability. From, you know, the very small eNPUs to the more powerful NPUs to the slices for the GPU, even using the CPU cores differently depending on power, latency, and memory capabilities. So, I mean, even though, I mean, correct me if I'm wrong, but this is a scalable architecture, and we're not pre-announcing anything here, but do you see any limits to that scalability at this point?
So let me take to before I answer that question, let me take you to why it's scalable. And if you were to look at Qualcomm innovation, is across all vectors of compute. Meaning, you see it obviously in the mobile phone, you see it on XR, pretty much invented XR, right? You see it on wearables. you see it in automotive, right? You see Qualcomm innovation across a very large level of compute devices and capabilities. It's super hard to do that in an efficient manner, cost-effective, efficient manner, resource. I always talk about time, talent, and treasure. You have to maximize your time, talent, and treasure. And in order to be able to accommodate all those devices, you have to think scalability. As if we think efficiency, power efficient as a centerpiece, one had to think about scalability, about another element on that centerpiece. Otherwise, you cannot deploy, right? If you had to do it for each one of them independently, it becomes too hard too soon, right? So that's the reason. Not necessarily that you want to do, as Eric said, well, it would be lovely if I make a 100 slices with 32 CPUs and, I don't know, 1,000 TOPS and 1 terabyte per second memory bandwidth. That will be an awesome device that you sell two.
Right.
Right? It's a correct supercomputer. You will sell two, right? It will be too expensive to do. Can that be done? Is it scalable? Is someone come up and say, hey, here are a few $1 million so you can build me one of those? You know, a few is a big, no, it's an understatement, right? Then yes, the market had to be there to justify. But it's scalable not because we necessarily want to get there. It's scalable because we had to be everywhere. Now, that doesn't preclude them, that we come up with something else, right? We certainly want to go across the market that we are entering with price points across the gamut. You see X2 Elite Extreme as our top ranking performance a device. We'll see what the market brings us, and if we start selling a lot of those, maybe we talk about going even further.
Look forward to it.
Absolutely. We have to talk a little bit about CPU cores before we wrap. I know we're running out of time. So as a second-gen product, obviously, and I know you haven't been at Qualcomm terribly long, but I'm sure you have some insight into this, is that there had to be lots of learnings moving from first-gen Orion to now Snapdragon X2 once the product was out in the wild and it was in the market. Can you talk about some of the key optimizations in the CPU cores that enable some class-leading single-thread and multi-thread on this latest platform?
I'm the least qualified to talk about this specific. Pradeep certainly is your man to do that. He did that very well today. But I will summarize things that we talk about today. It's not just one single thing. It's 100 things. I think, in my opinion, and this is not Qualcomm or anybody's opinion, in my opinion, the CPU architecture, the classic CPU architecture, is getting harder and harder to get optimizations.
Yeah.
Right? So it's not the one thing you can get 10% performance improvement. You need to optimize across a gamut of things. And by the way, when you optimize here, you have to change that. And when you change this, you have to optimize that. And when you optimize this, you're running out of frequency. Now you have to regress that and optimize for frequency, because as Pradeep was saying today, you can improve IPC, but and you give you 2% improvement, but you are hurting your frequency by 10. That doesn't work, right? Because you're adding clocks in your pipeline for the code, and that doesn't work. So it's really the compounded effort across many, many, many things. It reminds me specifically of a similar conversation in Microsoft when we were talking about improving the emulator. And we were talking about, what is the one thing that we can do to move from 60 to 75% performance of native? Right? And how we get it to farther. And then let's create a list. And there was nothing that we can identify that was more than 2-3%. We have plethora of things that were 0.5, 0.8, 0.2, 0.1, and we had to tackle it all, right? The team tackled it all. Similar here, right? It is all this little thing that need to happen, which makes it a lot harder, right? In terms of improving performance over time. And the result of that is this beautiful architecture that we had today, and beautiful in their complexity and their simplicity at the same time.
Got it. Awesome. I want to wrap up, Jim. Anything? Any closing thoughts here for Alberto?
No, it's just impressive. Thank you very much for the deep dive that we've gotten on the X2 architecture, and thank you for inviting us here to be part of it.
Oh, total pleasure. So we
Absolutely.
can do more.
Great conversation. Thank
you very much.
Thank you very much.
Really, thank you very much.
And thanks everybody for watching. If you enjoyed this conversation, please like and subscribe. We're trying to build the channel. We're a relatively new platform here, but Jim and I are doing our best to build it. The other guys, not so much. They're staying back home. And with that, I just want to thank you for watching. Thank Qualcomm for hosting us.